So today we spent probably half the time at the stadium. There's a saying, there's a phrase, Nullius in Verba. I don't know if I've talked to you guys about it before, but it's painted above my door at Norman High, and it's the original motto of the Royal Society. And the Royal Society was formed by the 1600s. Newton, I think, was the first president, and it was he was the first or second. Anyway, it was formed because the people that read and thought about things, had the time to do that, were getting tired of people having everything wrong, people believing in the wrong things, simply because it was dogma. Most from natural philosophy, most of the dogma came from Aristotle, right? He was from 2,000 years. People believed Aristotle. He was around 400 BC, and they were still believing it in 1600 AD. And so Nullius in Verba is Latin, and it translates to not by word of mouth, meaning that no longer are we going to believe something just because it's said to us. We're going to check it. We're going to verify it with instruments, and the best instruments we can make. Kind of going along the route of Galileo. Now, Galileo was gone by then, but and this Royal Society was formed in London. It's still there, by the way. My wife and I visited. They moved locations a couple times, but it's over there by Buckingham Palace. So Nullius in Verba is sort of what our philosophy is on physics, that instead of just accepting formulas, we should, if we can, with our very limited budget, if we can do something to verify it, we should. If modern society was more like that, we wouldn't believe something because somebody says it. We would ask for proof. And maybe we wouldn't be in the fix that we're in right now if people would not believe anything they're told. So that's Nullius in Verba, which has significance today as it did 400 years ago. So what we set out to prove today was, is the acceleration due to gravity on Earth 9.81 meters per second per second? That's what you see in books. Look it up. That's what it'll say. So we should be able to verify that. So in class, let me go ahead and I'll share the screen now. In class, we set out to do that. And so here we are, Thursday, 10th of December. Oh, by the way, black and blue is due in my box on my porch by 6 o'clock tonight. And that's black and blue from test 2A. Okay. There's a lot of tests out there. Test 2B, the take-home test, is also out there. It's also on porch. If you want to pick one of those up, Harrison was just talking to him a few minutes ago. He was out there picking up. We had a nice little chat. So then at the top, before you turn it in, write your blue score and your black score. It's not that I can't add them up, because it's just only 3 problems, but I'd like you to add them up so we can verify. And remember, blue score, you get half the credit back. Black score on that one black problem, well, 2 black problems. The first one, the last one, well, on part D for 7, you get full credit back. Okay. So here we are, virtual. So this goes along with sheet 215. And I don't know, I'm going to make my best effort to get through 216. I probably made a mistake yesterday going off on entropy, but if the class is interested and first hour dictates a lot of what happens, and first hour yesterday was unusually asking questions, so that gets me all pumped up, and we talked, and that's what happens. And the rest of the day, and you guys have to late last night, we talked about entropy, and we talked about the second law of thermodynamics. Not that that's trivial stuff. That's in the standards for understanding physics in high school. The problem with that is that now I've got to try and get through 215 and 216 before the end of the semester. I don't know how far we'll get on 216. If we don't, if we just get the front of it done, then we'll just do the back. No big deal. We'll just do the back when we get back from break. All right, so here we are on 215. We sort of looked at this, then we went on and did our own thing. We're going to come back tomorrow and fill in the gaps. So I guess with you guys, I'll just go ahead and we'll kind of fill this in. I can't take you guys to the stadium. I was hoping maybe a few of you could show up this morning, but we were outside. All right, it was safe. Anyway, so it says to write down the mass of the small mass ball, and the small mass ball is a tennis ball, and that is, it's 55 grams, so it's 0.055 kilograms. And then the large mass ball is a basketball, and that's about 550 grams, so that is 0.55 kilograms. So it's, and that I say that, I mean, some tennis balls are 57 grams, some basketballs are 570 grams, but they're about approximately 10 times the difference. Now, what you need to do is go to your garage or go to your sports room, and you grab a basketball, grab a medicine ball, grab anything and drop it. I can't really show it on camera, but you drop that basketball and you drop that tennis ball at the same time, which we did in class, from the ceiling, and they hit the ground at the exact same time. No difference. So after that, we did that in first hour. Then I said, we just did a demonstration in class. And I said, okay, that pretty much proves just visually that Aristotle was wrong right there. Nobody actually for 2,000 years actually checked. Aristotle said that the basketball would fall proportional to its mass, its size, and so the basketball should fall 10 times faster. It doesn't even come close. It falls the same rate. So because of that, I said, okay, we don't really need the tennis ball. We've already established that it's going to fall at the same rate as a basketball. So the basketball is easier to see. Let's just use a basketball. All right, so we use the basketball. And the first thing is free fall from a short height. And we measured the ceiling to the floor in room 807. And then we had to subtract the diameter of the basketball, because the basketball starts a radius away from the ceiling and it ends a radius away from the floor. And so it's the height from the floor to the ceiling minus 2r, or the diameter of the basketball. So first we measured the distance from the ceiling to the floor. Let's see here. And blah, 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 blah. Trying to find it here. There it is. So that's, let me cut this part out. I'll cut this part out and blow it up for you. Maybe. There. Cut this out. Okay. Move this over here. Blow this up. All right, so that's our data from one of the classes. From the basketball, 8.7 feet is ceiling to floor. So the basketball had a diameter, whoops, I don't know what that means. Oh, that's the circumference. That's the circumference of the basketball. Because I thought, well, it's easier, because when you're trying to measure the diameter of a ball, it's hard to, line it all up. So I had a tape measure, so I just measured the way around. Then we just divide that by pi, and that gives us the diameter. So the diameter of the basketball is 0.75 feet, okay? So then the distance that it falls is right here. So it falls, the delta Y in the classroom is 2.42 meters, okay, 2.42 meters. So over here, it says, forget the small ball. We're not worried about that anymore. I'm just going to drop it next year. How far will the center of mass of the large ball fall? We said 2.42 meters, I believe, just now. Okay. Then it says, starting with one of the orange kinematic equations, determine the equation for the acceleration of a dropped object free falling to Earth when you are given the delta Y at the end of the time. Now, this thing right here called free falling. First off, what is meant by free falling? Free falling means there's no air drag. No air drag. No air drag, no wind. That is technical, true free falling. Was there air drag in the room? Probably yes, a little bit. Was there air drag out in the stadium? A little more. Today was not windy. It was really calm. So we didn't really have wind to worry about. But there's always air drag. Air drag, remember air drag. Okay, hold on. Let's nip this in the bud. Because people will always say, oh, it's air drag, man. That's the reason. Air drag. No, air drag is RA equals 1/2 D rho A V squared. And so what this shows, and we've done a unit analysis on this, a gold standard, like a long time ago. I know you don't remember it, but this is a drag coefficient. Look it up in the book. This is the density of the air. This is the profile area of the basketball in this case, and that's the velocity. But when the velocity is fairly small, 3 or 4 meters a second, it doesn't make a huge difference. So RA is like here's RA. You put your hand out the window while you're driving your car, you're driving around a parking lot, you don't feel your hand blow back, then RA is negligible, right? In fact, even in a car, I think we say we don't even start putting the RA till about 20 miles an hour. We start putting an RA vector back when we get to free body diagrams. All right, so we don't have to worry about air drag. Let's just get rid of it. Forget that. So we're just going to go with the orange, the second orange, right? The second orange equation is the one that you want. Second orange. Boom, boom, boom. There. All right, so we have delta X equals V naught T plus 1/2 A T squared. Now we're doing this in the Y direction, so it's really not delta X, it's delta Y, but you get it. Now that V naught T, I dropped the ball from the ceiling. I didn't throw it down, so that goes away. So we're trying to solve for acceleration. I don't like that color, you can't see it very well. So acceleration then is, and remember, the acceleration due to gravity is G if it's in free fall. So really I'm saying G, quote, that is RG, is equal then to, I got to solve this equation here for A. So I multiply both sides by 2. I divide both sides by T squared. So I have 2 delta Y over T squared. And that's the equation we use to solve for the gravity, what we're saying G is, okay? So we say then that RG in the room is 2 times, and we said 2.42 meters divided by T squared. And so I had them, while I dropped the basketball, they all got their phones out and they're checking to see, where's it at? I'm trying to find some data. Okay, here, that's third. Yeah, okay, so here's some data from the timing in the room. And look at how wildly it varies. Well, by a quarter second. Because notice, big important thing here. Notice, it's going to come into play tomorrow when we go into this some more. Notice, all times are less than 1.00 seconds. All times are less than 1 second. That's important from what's going to happen tomorrow. So when you take, I had 6 sets of data, 6 people that felt confident enough in their times that they were willing to talk about it. And this is just 1 hour. They did it for every hour. And so when I do that, we get an average time of 0.88 seconds, okay, for this particular hour. All right, I just picked a random out. All right, so over here then, 0.88 seconds. 0.88 seconds squared. Now notice in the formula, if you had to get one of these, if you had to nail one of these things, be it delta y or t, which one is more important to be accurate on? I don't have chat pulled up, but we have 3 chats. Hold on. Oh, Evan said something. Oh, Evan, sorry. Oh, okay. Jacob answered you. Yeah, the gold standard is blue. Okay. Thank you, Jacob. All right. So now a question to you all, and you can put it in the chat if you want, but which one's more important here? Time or the height or how far it falls? According to the formula, which one do you definitely not want to make a mistake on? Oh, okay. So Evan said time. Jacob said time. So I agree, and I think I know why. Because we're squaring it, right? If you have an error in time, that error gets squared, and that's called a very important thing in physical chemistry. When you take it in college as a junior, this is called propagation of error, and you will fill up an entire blue book of propagating error. All these formulas you have to apply. That class, that was my favorite class. The lab was, oh my goodness, meticulous, to put it the least. You had to have like 4 or 5 sig figs in that lab, and that's hard to do. We're lucky to get 3. Well, we have this is a sig fig lab essentially. We have 3 sig figs here. We have the 2 on the height. We have 2. I'm pretty sure on that we're within 10 centimeters. I mean, we measured it very carefully, and that's probably my first iffy. So that's 3 siggies, and that's usually good enough for high school work and even undergrad work. But now the question is going to become, this will play a role tomorrow. The question is going to become, what about those 2 digits? Okay, we'll leave that there for now. So when you do the math here, what do you get for G? What do we get? Look at that. That's horrible. We got 6.25 meters. I think it's must be, I don't know if it's 3rd hour or 2nd hour, but that's bad for even our standards. So we get 6.25. So we're getting, I'm just going to skip the small ball. So we're saying that it's if we're taking that data, 6.25 meters per second squared. Somebody can punch that into the calculator and make sure that I'm not lying to you. Well, either there's less gravity in our room and we all feel light on our feet, or we made a mistake. Okay. So thinking that we probably made a mistake, we said maybe if we had more time and if we had more distance, we'd get better data. So we went to the stadium. Okay. And we forgot about the first hour, messed with tennis balls. And I said, finally, I realized there's no reason to mess with those. So we just went with basketballs. We took 5 basketballs, is all I had, 5 basketballs. And I sent 5 people to the top of the Harv. And then the rest of the kids all stayed down below. And then we dropped them. We said 3, 2, 1, drop. Okay. And then they timed it. And dun, dun, dun. Oh, by the way, the percent error we had was 36%. Nobody, not even a high school, is going to take that value. High schools should be within 15% at worst. Maybe 10% is better, but you get laughed out anywhere. You might as well just made up a number. Okay, so then at the stadium, first thing I did is I ran a tape, and we had somebody hold it, and we measured the height of the stadium. And in this particular class, I got 36 feet even. Other classes I got 36.4. Whatever I'm seeing on the thing, I'm saying. So there's some leeway. There's already some iffy stuff there. So in this class, we were saying that the height is 11.0 meters. In other classes, I was saying 11.2 meters. So, there's a little bit of a lag there because it kind of depends on where the person was. We were trying to keep the line vertical, but it's hard to tell sometimes. All right, I think the true answer is 11.2 meters, to be honest with you. So I'm not going to use 11. I'm going to use 11.2. Don't have third hours, don't matter. All right, so 11.2 meters is what we've had over the years. Okay, so now we're over, where we at? Dropped it 3 times. Okay, so this, we've already shown that. We've already shown this data. That was the numbers I was showing. Okay. Okay. We'll do this on Friday. We'll do this Friday, which means that actually we are going to be meeting Friday. We are meeting tomorrow at 4:00. I rode my bike yesterday, so it'll be rainy tomorrow. So I'll be sitting here. We'll be doing our 4 to 5 thing on tomorrow. So from a large height, how far will the center of mass of the ball fall to 3 siggies? And that's where we're going to put 11.2 meters. Okay. And it says how far. Oh, well, that was a small ball. Okay, forget that. Both of them are 11.2 meters. Small ball, large ball. We're just doing large ball, though. I'm changing this thing around for next year. There's somebody coming up now. If you're coming to get your stuff, why aren't you on the Zoom? That's all I'm saying. Maybe it's somebody from class. As I told them, they could drop it off later. Okay, so then it says drop each ball 2 times. We're not doing the small one. And we dropped it 5 times essentially. Since we've established in the room that everything falls at the same rate, well, the reason for that is we've not talked about that yet. It's kind of an interesting reason, but we'll get to that second semester when we get into more into mass and inertia. But anyway, the large ball, the large mass ball, we did it 5 times. So let's look at. Then I said, okay, establishing that they all fall at the same rate. I said, just give me all your times. And so when we got back in the room, this was I think 3rd hour. That's all the times they gave me. And I said, don't give it to me if you don't feel good about it. So these are the values they gave me for the amount of seconds it took the ball to fall from the top of the harv to the cement below. we used to drop watermelons. Then we dropped. I know we're so far behind because back in the day we were doing this around Halloween because we used to drop pumpkins and the kids would put candy in them and then candy would go everywhere. So I know that was Halloween time. We threw a chair off a big old desk off there once just to see what it did. And then we used to drop. We dropped bowling balls, and that's when they said you got to stop this asking because the bowling ball. We don't see what's a bowling ball do, because it's really dense. And so drop a bowling ball versus a tennis ball. They still, by the way, fell the same way. But the bowling ball cracked the cement down there. And then we used to drop golf balls. And so we dropped a golf ball, and there's cars parked there. Teachers parked their cars, and so we were dropping with the cars. But we dropped the golf ball, and this golf balls really bounced, and so it bounced up and it came back down and hit the hood of the car and put a dent in it. So we all took off running, and then I was looking back and I realized, oh man, that whose car that is? That's Tina Nation's car. She was the principal. So I hit the principal's car with a golf ball, and I thought, oh, kids say, don't tell her. I said, I gotta go tell her. So I went and told her, of course. I said, hey, I gotta fess up, man. We'll pay for it out of the cantina, right? Because I had money back then. And she said, she's cool. She said, hey, man, if it's for science, I'm okay with it. Isn't that cool? Now, that's a principle. Anyway, I'm sure Mr. Jackson would probably say the same. He's a cool guy. I mean, as far as that kind of stuff goes, he's an old science guy. He'd probably be cool about it. But so sorry about that. So here we are on dropping the basketball from the top of the stadium, and we toss the high and the low. The standard procedure. As long as you have at least 5 numbers, you drop the high and the low. I mean, it's preferred to have an odd number and then you drop the high and the low. And you could, if you're in a hurry, you just take the median at that point. But if you have time, so then we added these up. We added all. You could do this yourself. We added all these up here, and we divided by, it looks 7, and we got, for the overall, we got 1.35 seconds. Okay, so fill that in. Okay, so our overall time was 1.35 seconds. All I got to see from you, 1.35 seconds. Okay, we did that. And we're skipping the, okay, so then we're skipping the small ball. So then we got to find the new acceleration of the large basketball. And so we use the equation 2 delta y over t squared. We plug in 1.35 for t. We plug in 11.2. Let's do it. Let's go ahead and do it together then. So we plug in 11, because I'm going to change that a little bit. So, because I think I was off on the height. That's part of why the numbers aren't very good. A little bit. So our G, we're saying now at the stadium, is 2 times 11.2 meters. Divide that by 1.35 seconds squared. And what do you get? Somebody punch that in. What do you get? 22.4 divided by, you get 12.2. All right, so 12.2. Actually, I like the number better. Oh, well, 12.2. So here's the question. So we got 12.2 meters per second squared. So in third hour anyway, we have this wildly varying 6.25 meters per second squared. We're saying in the room, 12.2 meters per second squared out the stadium. And we ended up, okay, so this is our data from third hour. And we used 11, so we got 12.1. We got a little closer. And so we're looking at the percent error. Remember percent error? Yeah, we did this before, but it's the difference between the two values. If you have a known value, like I know 9.81 is supposed to be correct. Actually, we used a $50,000 accelerometer from OU, because when Dr. Witten used to come, he did a geophysics seminar. It would be an 8-week seminar with my kids. And part of the seminar was you would find the G, you'd find the gravity in the room. And so it takes like 20 minutes for that thing to level. But it would level, it would sit and think about it, and then finally it'd pop, not 20 minutes, about 10 minutes. It'd pop out a number. And we got that the acceleration in the room, I have the number written down somewhere, but I know the first 3 digits is 9.82. So it's not really 9.81 for us, it's 9.82, but fine. So the known value we're going to go with is 9.81, because that's what you find in a textbook. And so you put those there, then you take what you got and take the difference and divide it by that 10 times 100. So we're at 23%. Well, 23% error is better than a 36% error, but it's still just not going to work. That's not good for high school. Okay. So I think that's about where we left it. What else did we do? It doesn't take you guys as long because you're not walking to the stadium. So, okay. So here's how we'll leave it. We know we got a problem. We got to figure out why. And if you just look at these, just look at this. This might help you see why. Look at those values. Those are what we all the students, and these are young, these are old men like me. These are young 18, 17-year-old kids who have good reaction times. And they had their finger on the button. I mean, they're trying to do it right. And this is the values they came up with. You know, we took the average, but that's pretty big range. And then on the stadium, you think, well, now it's had time, you wouldn't get as much error. And those are the values for watching a basketball fall the same height. It should theoretically be the same number every time. And someone asked, well, what was there, updrafts? Or we checked the wind. There was a little wind, but it was horizontal. Okay, it wasn't blowing up. Well, updrafts will mess you up. I'm not gonna lie to you, but that was straight wind, and it wasn't even windy. Barely a breeze, even at the top of the Harv. So it was that was some of the calmest we've ever had it, and it was some of the worst data. Well, 12.1 isn't that bad actually. It's not terrible. So here's what we're gonna do. So tomorrow, see at the bottom here it says, and we do. I think the equipment. I checked it. I grabbed it at the end of class. Didn't have time to do it though. So tomorrow we're going to do, and I'll film it. I took a couple of pictures. I'll put those in the for you guys in just the stadium. But I'll film what we'll do tomorrow. I have a timer that goes to the nearest 10,000ths of a second, and then it's expensive. And then I have photo gates that are really good photo gates. And then I have a kit that you drop the ball through the photo gates, and then you'll have your exact delta Y, you'll have your exact time to like 3 or 4 cities, at least 3 cities. And then we should be able to look at that and get a lot closer to 9.81. So tomorrow we'll talk. Oh, and then we'll do something. That's why I said here, bring your dollars, because tomorrow we'll do the dollar bill trick. What good way to make some money, by the way. And we will we'll look at the photo gates and I don't have a whole lot of expensive equipment. This is some of the best stuff I have. And we'll look and we'll actually do some real calculation and see if we can get G closer to 9.81 with some decent equipment. Okay, so that's what's going to happen tomorrow. That's part of the thing tomorrow. And then we'll work. Oh, and the other thing we're working on is the back. We're going to be working on, almost done here. Oh, where's it at? Oh. Okay, let me show this to you. Maybe. There we go. So we're going to work on the back of this, which is measuring, actually quantifying how much error. Humans are not good. We are slow. It's nerve impulses move slowly through your head. If we were 30 feet tall and we stubbed our toe, it took a few seconds before we felt it because the impulse travels so slowly. So when you see something and then finally you react, it's slow. So we're going to actually quantify that tomorrow, and then apply that back, and looking at sig figs, realize why sig figs are important, why accuracy is important. And so we'll fill this table out. We'll do the thing with dropping the ball with photo gates. It'll be a good day. We'll do a little flashback and stuff. So it'll be a fun Friday. But I will meet you all, and I will meet tomorrow at 4. Okay, if you want to be here, and I'll tell you all about it. Okay, so bring that by 6 o'clock. You got about an hour and a half. Bring black and blue. Drop in the box. If you haven't got it yet, great. If you don't care about it, don't worry about it. If you don't do anything, you'll get 10 points just for leaving it in your slot. So if you got a 130 on it or something, I probably wouldn't do anything. Not worth it. Unless you're curious. All right. Let me turn this off. Any questions before we part for today? Let me see. We got Sophia, Conky, we got Rose, we got Evan, Jacob's there. Okay, good crowd, good crowd. Remember, next semester, we're still negotiating that this might be an actual hour of the day. So virtual kids have their own. I like it because I'll get paid more. Right now I'm doing all this pro bono, and much as I love you guys, I'd like to get paid. Okay, so hey, put a good word in for me. Tell administration I'm doing a good job. Man. They're thinking about paying me. It's insane. It's teaching for you. All right. Okay, then if you guys have nothing to say, I'll see you later. See you tomorrow. Bye-bye.